The purpose of this lab was to analyze the motion of a star orbiting a black hole of unknown mass to find the net force on the star and then estimate the mass of the black hole. From the provided position dataset, I used Python to iteratively compute dp/dt for all points, then used our knowledge of Newton's second law to compute the net force at each point. Finally, I applied Newton's law of universal gravitation to calculate the black hole's mass from the net force exerted on the star. My result was that the black hole has a mass of 2.9852 times 10 to the 31st kilograms. The CSV provided to me contained 1,460 XY position coordinates, separated by a time step of 86,400 seconds, or 1 day. The star's mass was provided at 1.9890 times 10 to the 30th kilograms. The unknowns we will be solving for are Fnet and the mass of the black hole, which we will ultimately solve for from Fnet. To calculate the net force at each point, we use Newton's second law in the form Fnet equals m delta v over delta t. To do this, we will need 3 data points. We first calculate v naught by dividing the displacement r1 minus r naught by delta t, where r1 and r naught are just the first 2 data points provided to us in the CSV, and delta t is our time step of 1 day. And calculate v1, the first velocity, from r1 and r2 in the same manner. Delta v naught is then calculated by subtracting v1 from v naught. The change in momentum is calculated by multiplying delta v by the mass of the star, and dividing this by delta t gives us delta p over delta t. We know from Newton's second law that this equals the net force on the system. By implementing this process into Python code, the computer completes the calculations iteratively for us. X displacement and x component of velocity are computed, and then the same values for y are computed in the manner discussed on the previous slide. These values are then used to construct an initial velocity at the index 1 previous to the current index and a final velocity at the current index. From this, we are able to calculate the initial and final momentum, followed by the delta v and the delta p. Here we utilize all of our calculations from the observational data and apply Newton's second law to link dp/dt to Fnet. Going further, we can describe the speeding up and slowing down of the star by calculating dp/dt parallel, which we know to be equal to the change in the magnitude of momentum divided by delta t and multiplied by p hat. Knowing dp/dt equals dp/dt parallel plus dp/dt perpendicular, we then calculate dp/dt perpendicular by subtracting dp/dt parallel from dp/dt. From our knowledge of Newton's second law, we are able to set Fnet parallel equal to dp/dt parallel and Fnet perpendicular equal to dp/dt perpendicular. It is important to note here that though dp/dt, Fnet, and their parallel and perpendicular components have the same values, they are not the same thing. Fnet and its parallel and perpendicular components are the cause of the speeding up, slowing down, and curving of our system, described by dp/dt. We relate their values through Newton's second law. Running our code, we can visually see the effect of Fnet. The black arrow representing Fnet parallel points along the direction of motion, initially pointing opposite to the velocity as the system is slowing down, and then transitioning to pointing forward as the system begins to speed up. The blue arrow, F perpendicular, is much larger in scale than the black arrow, indicating that the perpendicular component of Fnet is much larger than the parallel component. We'll see this a little later in our results. It points perpendicular to the parallel and towards the center of the kissing circle, which fits the curvature of the path. The yellow arrow represents our Fnet and always points towards the black hole. This checks out since we know the only force acting on the star is the gravitational force from the black hole, and we know from Newton's law of universal gravitation that the force on the star from the black hole points opposite to the position vector from the black hole to the star. From here, we can use Newton's universal law of gravitation to calculate the mass of the black hole. By plugging in our net force, gravitational constant, mass of the star, and the distance vector r, the distance from the black hole to the star, we can solve for the mass of the black hole. I did this iteratively within the calculation loop, as seen here, receiving a value consistent to 5 decimals of 2.9852 times 10 to the 31st kilograms. Now that we know the mass of our current black hole, were this hole replaced, but the motion of the star remained the same, could we calculate a new mass for this black hole? Is it possible that this mass would be different from our original black hole? No. The mass of the new black hole would have to be the same as our current black hole if the same motion was observed. We know this because we use the motion observations and our knowledge of Newton's second law and the law of universal gravitation to calculate the mass of our current black hole, so the same motion observations will always yield the same mass result. In conclusion, we can see that by applying Newton's second law, we were able to come up with a value of F net and its parallel and perpendicular components just from observing the star's motion data. We were then able to calculate the black hole's mass from Newton's law of universal gravitation and discovered it to be 2.9852 times 10 to the 31st kilograms.